Hello everyone. As Willie said, some of you will remember me as the ex-president of OUSAS. I've been involved with the society for 3 years, nearly 3 years now, and it's great to see such a diverse society that's evolved, and it's involved with so much. And I hope the newcomers among you will get to experience it and enjoy it the same way I have. So when Willie suggested that I give a talk to the society about the summer projects that she mentioned, like at Cambridge, which I just finished last week actually, I was very happy to do so. This is very recent and exciting work in a field that's just beginning to really develop as our computing power increases, as it does now, so rapidly, called near-field cosmology. We're at the stage where we're beginning to see so many questions and possible solutions unfold before us in this field, and also in astronomy generally. So this talk revolves around one of the more infamous questions in near-field cosmology called the missing satellite problem. So I start with a pretty picture, as all good astronomers should. This represents a typical Milky Way-like galaxy, but obviously we can't take a picture of the Milky Way because we're inside it. So this is actually the Andromeda Galaxy. It's a bit of a cheat that the media like to use when they like to represent the Milky Way galaxy, but it's actually the Andromeda Galaxy, which is the closest large galaxy to us, about 2.5 million light years. Everything is close. But you can see the two quite visible smaller, seemingly not star-like systems over here. And these are actually dwarf or satellite galaxies. They're bound systems themselves, but they're definitely part of the larger Andromeda Galaxy. Now, all you can see in this image is just luminous material and dust, the blocks of luminous material. Stars, in other words. What you can't see is the gas, hydrogen mainly, that will later go on to form stars. And most importantly, what you can't see is the famous dark matter. In fact, dark matter is tremendously important for explaining why all these satellite galaxies are formed, why even the Milky Way is formed the way it has. And so now I'll briefly explain why it's so important in this system. So, if you spent some time with popular astronomy books, you'll know that visible matter actually contributes a very small proportion of the total mass in the universe. Now, this is usually shown in popular books with a pie chart, but I found something a bit different. So, as you can see, you've got the major constituent dark energy, that's 70%, about. Cold dark matter, 25%. There's some invisible atoms like the hydrogen I mentioned before, 4%. And then this visible matter makes up less than 1% of the total universe. So there's a lot of it that we can't see. So the lambda cold dark matter model has been tremendously successful in explaining the structure and evolution of the universe that we see all across the universe. So here, lambda is the so-called cosmological constant, or what contributes to dark energy. That explains the expansion of space that we can infer today since the beginning of time, but more important now. And we can measure lambda's effects, the dark energy effect on the universe, using analysis of the cosmic microwave background radiation that we can see today. So to measure this dark energy, we can look at how homogeneous the whole universe is, as far as we can see. So this is a temperature map from European Space Agency's Planck mission, one of the more recent missions, which shows the Milky Way very nicely. So all this bright, I don't know if you can see it very well in the light, but all this bright galactic plane here, all these blue bits, that's all the Milky Way. But beyond the Milky Way, you can see quite a homogeneous distribution, not much colour variation, and in fact the temperature varies by 1 part in 10 to 100,000. So very, very small temperature variations. And so this tells us how homogeneous the universe is in between space. And in order to get this, we need to invoke a certain amount of dark energy in order to explain this. Now, the other part of the NASA CDM model, CDM bit, is the cold dark matter. Known as cold because it's non-relativistic, it travels relatively slowly. Unlike the hot dark matter theory, which we don't really use that much. There is some mixed matter theories that go around, but in terms of describing galaxies and stuff, we use cold dark matter theory. And we can detect dark matter through its gravitational effects, but nothing else. We can't see it, it doesn't give off light. That's why it's called dark matter. But we can detect it through its gravitational effects. And so we can map the distribution of dark matter using its invoked gravitational effects. So I'll leave the rest of the explaining to this video, which should hopefully play, from NASA and the European Space Agency. So that's a big point. Really, do you know the first point? Yeah.
Anyone know what it is? I have a feeling they're answer pieces. I'm thinking broadcast by that before. Well, they're supposed to be, but I don't think we've been able to
This is focus.
The stars and galaxies we see in the night sky represent only 1/6 of the total matter in the universe. The remainder is a mysterious component, dark matter, that neither emits nor reflects light. So, for astronomers, the challenge of mapping the universe has been similar to mapping a continent from just the lights of the cities. For the first time ever, astronomers have been creating a three-dimensional map of how this dark matter is distributed across the universe. To this end, an international team of scientists, amongst them groups from Marseille, the Max Planck Institutes, and Paris, have been using data from the NASA-ESA Hubble Space Telescope. The results are published in Nature Online on the 8th of January 2007 and at the meeting of the American Astronomical Society in Seattle. Although the invisibility of dark matter makes it hard to detect and has eluded scientists for decades, the team of astronomers led by Richard Massey of the California Institute of Technology made this map after years of painstaking analysis of the Hubble Cosmos survey, the largest survey of the universe ever conducted from the Hubble Space Telescope. The map offers a first glimpse of the web-like large-scale distribution of dark matter in the universe. The map reveals a loose network with a sponge-like structure of long filaments intersecting in massive condensations where clusters of galaxies are located. The survey encompasses an area of the sky 9 times that of the full moon and was carried out by an international team of 70 astronomers led by Nick Scoville of Caltech. The exceptional image depth and resolution of Cosmos has made it possible to cover the large areas spanned by the dark matter structures and to obtain details of its distribution. Currently, astronomers can best probe dark matter by using gravitational lensing techniques, which is the bending of starlight caused by the presence of dark matter in the universe. The map was created by using this technique and analysing the distorted images of 500,000 distant galaxies. Such subtle distortions were then used to reconstruct the mass distribution along Hubble's line of sight. Stretching halfway back in time to the beginning of the universe, the map reveals a network of dark matter filaments collapsing under the relentless pull of gravity and growing clumpier over time. The map shows how normal matter, including stars and galaxies, assemble and clump on top of the densest concentrations of dark matter. The three-dimensional map is a historical achievement in its own right, since it enables astronomers to better understand how galaxies formed and grew, and has at the same time accurately confirmed current theories of how such structures came into being. This result from the Hubble Cosmos survey has given us unprecedented information about the distribution of dark matter. Future improvements may lead to insights into what dark matter actually is, for instance the exotic particles that some scientists suggested many years ago.
There we go. So that's an example of how we can infer dark matter's presence in its gravitational effects. And we can do just in a similar way with the Milky Way and the Milky Way. So why is this important to us? Well, the Milky Way contains about 10 times more dark matter than it does normal matter. And dwarf galaxies, more like 100 or 1,000 times more dark matter than normal matter. So clearly, it's pretty central to whatever statistics we want to run on our dwarf galaxies. So, as it turns out, each galaxy is, and this goes for dwarf galaxies and large galaxies alike, is embedded in a large dark matter halo. So this whole region here. Spreading over a volume many times the size of just the distant parts, which are inside here. So, with the halo being its most dense at its core. These dark matter halos allow the visible matter to be contained in a very large gravitational potential well. Over time, different galaxies and their halos merge, causing their dark matter halos to overlap. But because the luminous cores are in a position so dense, so in a gravitational well so deep, they can survive this clustering process. And their identities are preserved as they go on to form part of large systems, such as the Milky Way. So this explains very nicely the existence of Milky Way-sized satellites and also predicts the existence of dwarf galaxies. Great, so we're done, right? Very that simple. When we do run our simulations and try to get the right result, it turns out that we get about 1,000 dwarf galaxies. And when we look at the sky, as of a couple of years ago, we saw 11. A bit off, even by astronomical standards.